Good morning. In the previous lecture, I started to argue that the most important fundamental thing determining all of its other properties of a star is its mass. But before I explain that further, it has something to do with what happens in the center, right in the middle of the star. Before I do that, I want to start out with the one star that we have the most information on because it's our nearest neighbor star. It's just, what does it say here, 150 million kilometers away. One astronomical unit away from us, we can look at our own sun. It's a perfect star to study in many ways because it is so completely ordinary. It's by no means the hottest surface temperature star at 6,000 centigrade. It's not the coolest surface temperature star. It's in the middle, and it has a very typical mass and a very typical size. Many other stars like it, billions of other stars in our Milky Way galaxy alone. And so we can maybe get some insights from what must be happening in the center of our sun that will apply to all of the rest, most of the rest of the other stars in the Milky Way galaxy, and presumably throughout the universe, which is made up of galaxies of stars. And so you don't really need to memorize these numbers at all. I'm not that concerned about them, but there are two interesting numbers I put up here that might surprise you. They surprised me when I first saw these. Of course, we know from Newton's law of universal gravitation exactly what the mass of the sun is. That's a lot there. 2 times 10 to the 30 kilograms. Obviously, scientific notation essential to sort through these problems. And then the size, of course, is vast compared to Jupiter. 700,000 kilometers in radius. You can pack, I don't know, 1 million Earths in there. You can pack a lot of planets into that. You can pack 3 Earths into one of these sunspots here in this picture. So this is an enormous size, but it's also an enormous mass. By the way, I have to let you know, I don't know how many pictures I've seen of a yellow sun. That is wrong. If you take a true color photograph of the sun, it is not yellow unless it happens to be setting when the light has to pass through an unusual amount of gunk in our atmosphere. Normally, if you take a picture of the sun, it looks exactly what color? White. If you want to know what color the sun is, look at a very good reflection of it, which uniformly reflects all of its colors, which is off of fresh snow. Fresh snow has a very uniform reflectivity, and you can see what color the sun is there. It's about as white as freshly fallen snow. Again, it's right, in other words, in the middle of our visual color range. It's right in the middle of the wavelength range that our eye is sensitive to. Of course, that's not just a fortunate coincidence. It's a result of natural selection and evolution. Not in this course. Getting back to the mass and radius, it would be very easy to work out the volume of a sphere. It's very close to a sphere here. That's just a 4 pi over 3 r cubed. And I'm not going to make you do that right now, but then we would know what the volume of the sun is, and then we would divide that into the mass. We get a mass per volume, which is density. So then we could work out how many grams per cubic centimeter is the sun on average. And at first glance, you might think 1.4 grams per cubic centimeter. That doesn't seem so unusual. That's like the density of things around here. That's just a little bit more than the density of water. So it's not really out of the range of densities that we're already familiar with on Earth, except there's this one kicker. The entire volume of the sun is gas. There's no water. There's no liquid in there. There's no solid in there. It's too hot for that. It's entirely a vaporized gas. And now I'm telling you that the average density of the sun is gas, but it's a gas that's about 10,000 times denser than the gas in this room. My gosh, and in fact, it's even much, much, much denser in the middle, where all of the gravity is crushing it down to the center, because there's an enormous surface gravity. You could work out what the surface gravity here is, and that'd be an interesting problem. Figure out what your weight would be on the surface of the sun. Not that you could exist there for more than a microsecond, you'd vaporize, but if you could be there, it turns out that most people in this class would weigh well in excess of a ton on the sun. All right, so that is a lot of gravity, and that is why the gas is compressed to such ridiculous densities that you could never even imagine gas being like that condition anywhere around the Earth. It's really beyond our experience. And as we said before, we got the two basic factors of the sun that you can measure from the outside, that you don't have to be inside to figure out. The surface temperature that we measure in detail from studying the spectrum of the light from the sun, and then the luminosity that we know, remember we worked it out, it's just the brightness of the sun times 4 pi times the distance squared. All of these are known very, very accurately, and these are very big numbers, but not big for stars. All right, so what can we infer from these numbers? Well, the first thing you might be wondering, and I think this is the big key question, a major question for this lecture is, well, Matt, you just told me that the sun has so much mass that the gravity is crushing it. Even the surface gravity of the sun is just so intensely strong, it must be crushing and crushing that gas down into the center. What's keeping it from collapsing right now? What's keeping the sun stable? There must be, of course, an opposing force. Whenever you see one very crushingly strong force of gravity pushing in, if nothing is collapsing, if there's no acceleration, Newton tells us the forces must balance to zero. So there must be an outward force which is very strong, equal, in fact, to the inward force of gravity. Let's see. Can I just ask another question, though? This is a similar kind of question. The Earth doesn't have nearly as much surface gravity as the sun, but still, it is a lot of Earth here. There's a lot of rock and mountain and so on, crushing down towards the center of the Earth. That's the center of gravity. Why doesn't the Earth just collapse under its gravity right now? I hate to scare you guys. I feel bad about that afterwards, but I'm trying to make a point here. There must be an equally strong force inside the interior of the Earth, which is pushing back out, and basically it's the pressure exerted by very dense rock when you squeeze on it. Oh look, I do have a piece of rock here. All right, you can squeeze on this, and the harder you squeeze on the rock, the more it pushes back. My fingers are getting squished by the force back out. So rock has a tremendous amount of strength, which it turns out is enough to hold itself up against the inward force of gravity, and there's a balance between the outward pressure of the rock and the inward pressure of the inward force of gravity. That force wouldn't be strong enough on the sun. If you make rocks, I don't know, 10 times more massive than this, and you make the forces that much stronger, this stuff is going to start getting crushed and liquefied, and the Earth would, in fact, start collapsing. Until something else would happen, until a larger pressure would build up to reach some kind of equilibrium of forces. The equilibrium we're looking for here that is found in just about every astronomical object in the sky, whether it's Jupiter, whether it's a planet, whether it's the moon, whether it's the sun, whether it's any star, in any galaxy, the balance between the inward force of gravity and the outward force of pressure is called gravitational equilibrium. In the old textbooks, we used to call it hydrostatic equilibrium, which is just a jargon term for astronomers that confuses the issue. Well, what is the outward force of pressure in the sun? I said it's not made of rocks. They're not strong enough. They would be crushed. It must be something stronger. It's just something we are familiar with. It's simple gas pressure. Gas pressure. Well, we've certainly seen gas pressure, for example, that keeps your tires inflated, holds up your car. That's pretty impressive. A little bit of gas can hold up your car. That's pretty heavy. But remember, that is a rather low density of gas that's in your tires. What if you were to inflate your tires, I don't know, 10,000 or 100,000 times more air? Of course, they're not that strong. Then you'd have 10,000 or 100,000 times more gas pressure. That still wouldn't be very much. Now, here's the kicker then. It's not just the gas pressure's proportional density, it's also proportional to the absolute temperature of the gas. That's right. So the gas in the sun, which is very dense to start with, the pressure, of course, is what's it caused by. Let's think about this microscopically. You have lots of little gas atoms. They're mostly hydrogen, some heliums, and they're moving around and bouncing into each other boom, 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 all the time. You can think of them as little marbles that are bouncing and ricocheting off each other, and many, many, many times a second. Now, all of these collisions then are confined into the sun, but of course there are collisions going outward from the center of the sun, and every time a gas molecule bounces like this and bounces back, it transfers a little bit of momentum outward. It's trying to. So a transfer of momentum is basically equal to a pressure. So the little microscopic collisions of all of these atoms, they're not molecules. It's too hot to have molecules in there. They're broken apart. But all of these little atomic collisions are pushing outward from the center. The center is the densest. And so you can see from that simple little illustration with my little fingers, because I don't have a graphic to show you this right now, that the gas pressure will increase if they're moving faster. Right? If they're going much faster, there are more frequent collisions, and each collision gives a larger kick. There's more momentum pushing out. So the gas pressure goes up with the temperature. I mean the temperature as you measure it in absolute degrees, above absolute zero. The only temperature at which a gas exerts no pressure is if you can cool it all the way to absolute zero, which, forget that for the moment. The only place that that's happening is out in the space between the galaxies, where it's getting pretty close to absolute zero. But in the interesting parts of the universe, the temperature is much higher than that. And so it was deduced really in the early part of the 20th century correctly by people who just knew gravitational equilibrium and they knew gas pressure. It's all they needed to know. Sir Arthur Eddington in particular was able to work out, well, I know what the temperature is in the center of the sun. It has to be about 15 million degrees centigrade, or 15 million degrees Kelvin, the absolute temperature scale. They only differ by 273 degrees. So we'll just call it 15 million degrees. How did Eddington know that? He'd never gone there. Nobody's ever going to go and visit there and take a sample of the core of the sun, measure its temperature. He didn't need to. That's the temperature that it would have to be to produce enough pressure to balance what we know is the gravity. It's basically just gm over r squared that's crushing the sun. That's gravitational equilibrium. Now, I wonder if you might be worrying about another problem now. That is a tremendous temperature. That's a tremendous amount of pressure. If I had a little ball from the center of the sun right now that would be a density maybe thousands of times the density of water, in the core it is, that'd be a ridiculously dense ball of gas, and it were 15 million degrees, well, first of all, we'd all be vaporized in a second because it would produce so much radiation. It's so hot, we'd just be vaporized in gamma rays. But the second problem is that it would immediately explode at some fraction of the speed of light. So, now I just told you that that is the condition throughout the entire core of the sun. Are you worried that the sun might explode in the next few minutes? I'm really trying to scare you today. Well, we still haven't seen the sun yet here. And of course, we're only looking at it as it was 8 minutes earlier. But at least I can tell you as of 8 minutes ago, there's no evidence that the sun has exploded, even though there is an explosive force of this ridiculously high gas pressure. And don't worry. Don't worry about all of these things I've been troubling you with. Is gravity going to be too strong? Oh no, it collapses. Is pressure going to be too strong? Oh no, it explodes. You know, the beauty of this is that gravitational equilibrium is almost always obeyed in the sun throughout almost all of its lifetime, and all stars besides the sun also. They always manage to adjust themselves to be in hydrostatic or gravitational equilibrium. Isn't that nice? Does that seem like the hand of providence? No. It's just physics. Actually, things in the universe almost always want, when the balance forces start out unbalanced, they almost always want to balance themselves up very quickly by adjusting things. And that's exactly what happens in stars. If, for example, let's suppose that gravity was winning. Let's suppose that gravity was 1% stronger than gas pressure. What's going to happen? This would happen very quickly. The sun would get squished down, a little bit more compressed by this extra gravity, and then what would happen in the center? Compression, just like happens in a diesel engine, when you compress gas, it gets hotter, denser and hotter, so the pressure would go up. The pressure would go up until gravitational equilibrium was achieved. It's going to naturally be achieved. What happened if the opposite occurred, that the temperature was too high in the center of the sun and the pressure started pushing out and winning over gravity? Don't worry about it. In a short time, I guess a few thousand years or whatever, the sun would actually expand a little bit because pressure would be winning a little bit. Then what happens? Well, if it's a little bit bigger, the distances between the masses are larger. But the main thing that happens is that the pressure goes down. The density and temperature cools off a little bit in the center. Either way, it always establishes gravitational equilibrium. That's obeyed through almost all of the lifetime history of the sun and other stars. You can count on that one. You can take it to the bank. So this temperature, we really believe, must be quite accurate. So we know what the center of the sun is. So now that raises an interesting question. What's going on in there to generate, what was that huge number of watts? 4 times 10 to the 26 watts of power. Darn, that's a lot. So the original ideas referred to power generation sources that 19th century physicists already knew about. Chemical energy, chemical reactions. For example, what if the sun, it is a very big ball of fuel, what if it were entirely made up of refined petroleum, gasoline? I know that's a pretty crazy idea. How did it get there? What put it there? But something like that. Well, there is a lot of energy in a gigantic ball that size of gasoline, especially if it's jet fuel. And in fact, it could, if you set it all on fire simultaneously, it could produce 4 times 10 to the 26 watts, I suppose. I mean, it's not out of the realm of possibility. All of that could be produced by some kind of chemical reactions. Remember, chemical reaction is just when the atoms, the center of the atoms, the nuclei are untouched, but electrons are reorganized and reshuffled, basically by molecules making and breaking electric bonds. That's something that happens way outside of the nucleus, so it doesn't give you that much energy per atom, but it would be enough. But here's the problem. Which only gradually became clear that it was a problem. You do have enough fuel to produce the huge amount of energy we see at the moment, the power, but only for a limited amount of time. And now we know that that's actually very limited. It would all run out, it would all burn out, all of the chemical energy would be exhausted in about 100 million years. That sounds like a long time. What's the problem there? Well, it became a problem when people started looking at the age of the Earth, and particularly the age of Earth rocks, by using this new, very impressive, exciting technology to measure radioactive elements which have long decay times in the rocks of the Earth's crust. And they realized, these rocks have been decaying. In other words, they've been rocks. They've been solidified into the Earth's crust for much more than 100 million years. The Earth, and then by implication the Sun, has been stably sitting here for billions of years. We have fossils that are more than 100 million years old. We have fossils of leaves of plants and things and trees or whatever that were more than 100 million years old, so they were obviously enjoying plenty of sunlight way past the time in which we would have run out of any chemical energy. So that's impossible. Another idea, which was even less of a good idea, was, well, maybe the sun is not in an equilibrium state and it's gradually collapsing. Well, again, the problem with that is it would have collapsed after 10 or 20 million years, and yet we were finding out in the 19th century that the sun is much older than that and has been around happily producing energy for billions of years. So a much more efficient way of producing energy from the given amount of fuel in the sun was needed, and astronomers, not really anybody else, started deducing that the real energy, for example in hydrogen, the real energy of a fuel is if you can make changes to its nucleus. That's where all of the forces are the strongest, so if we rearrange things in the nucleus, enormous energies could be released. Wonder how we would do that, though. Well, that's the interesting question. Now, around the time, the turn going into the 20th century, it was realized by Einstein very famously that if you have a nuclear reaction, so the forces are enormous there, the potential energies are huge, I want to get energy out. The way to do that would be to have a reaction which puts in a certain amount of mass, and then at the end of the nuclear reaction, the nuclei actually change. They change their elemental composition, and the products of the nuclear reactions end up having a slightly lower mass than the inputs. Oh my gosh, what a radical idea. I thought that we learned in 10th grade chemistry class, was it 11th grade, that the total mass of a system, such as the sun, is always conserved. Isn't that right? It can change its form, solid, liquid, gas, but the total mass, which we tried to measure in those difficult experiments, was always conserved in any chemical reaction. Ah, but you weren't, hopefully, doing any nuclear reactions in your high school, unless it was more radical than mine. It takes a lot of energy to start a nuclear reaction, or a lot of force. And in a nuclear reaction, what we find is that the mass that you end up with could be smaller or larger than the mass you started with. That's not necessarily conserved. What is conserved is the total mass plus energy of the system. And what kind of nuclear reactions do you think we're talking about? Well, the astronomers had a pretty good hypothesis. They figured that hydrogen was the most dominant, abundant nucleus in the center of the sun, and they knew very well that if two hydrogens are going fast enough, meaning that they have enough momentum, meaning that the temperature is high enough, they will get so close. How close? They will, on a head-on collision, or nearly head-on collision, they will get so close before the electric repulsion of the 2+ charges knocks them apart. They will get so close that they are approximately the same separation as 2 protons are inside the nuclei of other atoms, such as, for example, helium, which has 2 protons in its nucleus. So if you could just get the 2 protons that close together, even without this being understood 100 years ago, it was still evident that there's some other stronger force. We now know it's a strong nuclear force, which will grab hold, only acts on this very short distance. Over a short scale, it will grab hold and it will fuse them together. We're talking about a nuclear fusion reaction. That's the plan here for how the sun could produce all of the power that it is currently producing and has produced over its entire history of 4.5 billion years. As you can see, the whole game here to getting a nuclear fusion reaction to take place is energy or speed or temperature. That's why it's called a thermonuclear fusion reaction. We're going to need ridiculously high speed, high energy, high temperature collisions to have a chance to make this happen. And it was immediately obvious that any temperature below 10 million degrees was not going to cut it at all. That's why it's hard to make a nuclear fusion reaction occur, which is probably on the whole a good thing, or else humans would have been destroying a lot of stuff a lot earlier than we were. It takes a little bit of energy to start a chemical reaction like a fire, but not too much energy. It takes a lot more energy to start a nuclear fusion reaction. And so without knowing the details of this, Arthur Eddington and a few other astronomers deduced that the conditions must be right for this to take place in the center of the sun. They already knew that there were bare protons. See in my diagram, that's a single proton there flying, and there's another one flying at high speed. Geez, wait a minute, I thought it was hydrogen. What happened to the electron? At these high temperatures of millions of degrees, the collisions were already so violent between hydrogens that the electrons were knocked free. They were collisionally ionized. In other words, we have a totally ionized sea of individual plus charges, such as atomic nuclei, like protons, and they're floating around in a sea of very high-speed colliding electrons. A fully ionized plasma is what it's called. It's not really exactly a gas. You could sort of a complicated ionized gas. You could call it a fourth state of matter if you want. I don't know. Anyway, clearly the centers of all stars have to be fully ionized plasmas. So we're only interested, though, for the moment, in the collisions between the nuclei, between, for example, the protons here. Don't worry, electrons are colliding with each other very rapidly too, billions of trillions of times per second. But this is the interesting collision here, a head-on high-speed collision between two protons so that they can fuse. Let's see. Just so that you know this is quite different from the other kind of nuclear transformation you could happen, the one that humans mastered first because it was a bit easier, not too easy, but a bit easier, because it didn't actually require a high temperature. That's fission. Fission is exactly the opposite of the fusion reaction I was just describing here a second ago. In fission, you start with a very large atomic nucleus. That maybe is so large, it has so many particles in there, so many plus charges, that it actually may be slightly unstable, or you can make it unstable, and it wants to split apart into smaller pieces. When it does split apart into smaller pieces, if the, this is the opposite of what I said before. It's the same deal. If the mass of the pieces coming out is smaller than the mass of the piece that's split, then a little bit of mass has actually changed its form. It's changed from mass into, you've got it, energy. And what is the conversion formula when you have a certain amount of mass that is transformed? How much energy do you get? It's Einstein's famous formula, E = mc squared. Actually, that formula works in both of these, a fusion reaction and a fission reaction. In a fusion reaction, as we'll see in a minute, you can add up the masses of all of the hydrogens that go in. Then you can compare that to the mass of the helium nucleus that comes out, and you will find that there is a slight deficit. A little bit of mass has, quote, gone away. Quote, disappeared? No. It has converted itself. It's been you multiply it by c squared, that missing that converted mass, and that's all appears as energy. And since c squared is big, c is the speed of light, the square is huge, a little bit of mass produces an enormous amount of energy. Anyway, it's just interesting historically to know about fission nuclear reactions or their radioactive decays, because that is the basis of current nuclear power. It's the basis of atomic bombs and so on. They're fission bombs. And it's fortunate that these are fairly difficult to produce also, because you have to have a very high quantity of relatively pure fissionable material with just the right properties. Yes, you've heard that uranium will do it, but actually the good kind of uranium that does these fission reactions very effectively and could do them really rapidly, so that one fission reaction would release neutrons, which would trigger 3 or more fission reactions to then reduce 3 more neutrons, and it makes a chain reaction. That only works with uranium-235, a rare isotope, which is extremely difficult to separate from the normal uranium-238. And so that's why basically nobody thought anybody could do it in the 1940s. Except miraculously, we managed to do it. The Germans were poking around at it. The Japanese thought it was completely hopeless. Manhattan Project, amazingly, it's probably almost as amazing as the Apollo Project, actually managed in a few years to purify and separate a fissionable amount of mass. It's about this much mass of uranium-235 and produce, well, basically just about two or three atomic bombs to end the war and actually save millions of lives of innocent people, it turns out. All right. So let's get it back to thermonuclear fusion, though, because this is keeping all of our lives going here. This is the energy that powers everything on Earth. Let's look at the reaction in a little bit more detail here. It's a multi-step process. So first we have two protons hurled together in a very high-speed head-on collision. And this is an interesting point I'll just mention here. Even though Arthur Eddington had worked out what the temperature in the center of the sun was, and even though he knew that a collision at that temperature would bring the protons fairly close together, he was also a good enough scientist and mathematician to realize actually at that temperature the protons do not actually come close enough together to touch. They're actually a bit further away than protons are in a nucleus of a helium atom. So there was this problem that the temperature seemed to be a bit too low, the temperature he worked out, for his idea, it's a very attractive idea, of a hydrogen fusion to be happening. But he knew he had to be right, and there was just something missing in his calculation that made the situation a little more complicated than he said. And this argument got kind of nasty, at least in a sort of a scientific sense, and there's a very famous exchange between Eddington and his critics. And I love what he said. He was trying to diss them, and he said, well, you know, some of the people have argued that the conditions aren't right in the sun for these reactions to actually take place. My response to these critics is I suggest they just go and find a hotter place. Oh, Arthur, what a put down. He's telling them to go to hell, isn't he? In a very scientific way. I love that. He turned out to be right, too. It helps if you're going to win these arguments. And in fact, what had to be included in this is the uncertainty principle coming back. Yes, it's true that if two protons are a near distance from each other, they're not actually stuck together in a nucleus. But remember the uncertainty principle. Protons are not little billiard balls bouncing around. They're uncertain clouds of probability distribution. And so even though the protons usually are fairly far apart, there is a small but finite non-zero probability that the probability clouds of these two protons, here's my great illustration, may have a little bit of overlap. It's a statistical process. You can't predict exactly which ones are going to fuse, but the uncertainty principle says that yes, if you collide enough of them fast enough, frequently enough, at very high speeds, a few of them will actually, due to the uncertainty principle, find that they're stuck together. So that's how it works. Eddington was right. It's not a hotter place, but the uncertainty principle allows these reactions to occasionally happen, and that's enough to keep the sun alive, to keep us alive. But then all you have, what's happened at that point? You've got two protons stuck together. One of them very, well, all right, that looks like the beginning of a heavy nucleus, but it's not really anything normal at the moment. So we need, if we want to get to helium, we need more atomic nuclear particles. Now remember, helium has 4 particles in its nucleus. So far, we've only had 2 of them stick together. So because you have a high density and because collisions are happening frequently, after you have this little pair of nucleons together, there's a very good chance that a third proton will hit here. And so at that point, actually 2 of them have converted into neutrons. So what you have at the second step here is you have 1 proton with 2 neutrons stuck together on it. That's a very heavy hydrogen. It's tritium. Still not anything stable. So finally, in a rapid succession, a 4th proton has a chance of hitting and sticking, and then you have 2 protons and 2 neutrons. You have the nucleus of a helium-4 atom. So the net effect is that 4 protons came together, and what came out was a helium nucleus with some interesting transformations. Well, let's see. 2 of the protons actually got converted into neutrons. Now that's a sort of an interesting reaction there. I thought that electric charge, total electric charge, would be conserved. And yes, you're right, it should be. So you can't just have a proton converted into a neutron. You have to take the plus charge that the proton had, and it gets deposited in a newly formed positron. Wow, what the heck is a positron? Positrons, only discovered in the 20th century, they're in every way essentially identical to an electron. Same mass, same electric charge, same properties, except that it's a plus charge instead of a minus charge. They're the opposite of an electron charge. Actually, if you look at the equations for a positron, it's pretty much the equation of an electron going backwards in time. But you don't need to know that. Anyway, a positron, like I said, is the first form we've seen of what I'm going to call antimatter. These are particles which actually do exist, which have identical properties to normal matter, such as electron. I'll call that normal matter. In every way, same everything, except the opposite charge. So now I wonder how come there are very few positrons, probably none, in this room right now. In fact, why is antimatter virtually non-existent in most places in the universe today? Because, as you well know, it would have a very short lifetime when it's created. The instant that an antimatter particle, such as a positron, is created, it's going to be in danger of having a collision with normal matter, such as an electron, of which there are lots of them around. And the instant that an electron hits a positron, you know what happens? Total annihilation. All of the mass of the positron, all of the mass of the electron disappears as mass and is converted into energy. The famous formula, E equals mc squared. So even if you didn't care about what's happening with the helium, the mere fact of producing these positrons would give you a lot of energy in the process. Also, there's a little more energy given whenever you have a reaction like this that changes a proton to a neutron or back. You're not using the strong nuclear force. These reactions take place because of the weak nuclear force. I told you that that fourth force of nature was important, that it does some really significant things. This is the most significant thing it does. It can convert the proton into a neutron so we can eventually synthesize helium-4, nuclei in the center of stars. But one other particle is produced that also has some energy, and that's called a neutrino. Very interesting particle. We'll come back to that later. It's neutrine. That means it has no electric charge. It has no interactions with matter involving electric or magnetic fields, and it has no interactions with the strong nuclear force. In other words, it's very uninteractive. And so the neutrinos will leave the center of the sun in a straight line at darn near the speed of light. In a few seconds they're gone. They're just out of there, as I mentioned before, because there's only weakly interacting particles. All right, so these don't get a lot of attention. But we could actually try to detect them with a very elaborate laboratory on Earth and see if these nuclear fusion reactions are taking place currently in the sun as we predict that they are. We could actually do an experiment here to test that. So to summarize all of the things that go into nuclear fusion reactions in the sun now, it's called the proton-proton cycle, but you don't need to know the name. In a series of steps, you don't even really need to know the steps. 2 protons hit and stick, then another third one, then a fourth one, and what comes out is a 2 proton, 2 neutron helium nucleus, 2 positrons, and some neutrinos, and a lot of gamma rays. A whole lot of gamma ray energy. And these positrons, remember, everything has to stay electrically balanced in the center of the sun with the same number of plus and minus charges. So clearly, now that a helium nucleus has come around here, there's 2 electrons floating around in the plasma that no longer have protons to go with them, and so they're going to very happily collide and annihilate with these positrons in very short order, giving off even more gamma ray radiation. So these reactions then are taking place at such a high rate that 4 times 10 to the 26 watts, largely in gamma rays, is being produced in the center of the sun. That is a whole heck of a lot of energy. And the remarkable thing about it is that the sun has enough hydrogen there that it can keep on doing that for many billions of years, because this fuel generating power is far, far, far more efficient than any chemical reaction. It's, let's say, about 1,000 times more efficient. So the sun can keep burning at its current rate of power output for thousands of times longer, as we'll see later. All right, so just how much energy are we talking about here from this multi-step nuclear fusion process? Well, you can actually look this up in your textbook here. I have a textbook here, and it has the mass of a proton in atomic mass units. You can look that up. This is basically the nucleus of hydrogen. So 4 hydrogens is 1.008 times 4 atomic mass units. That's 4.032. Then if you look down to the second entry, you need to look at a periodic table. The second entry in your periodic table tells you the mass of a helium in these same atomic mass units. The atomic mass units are about the mass of a proton here. And helium is 4.002 atomic mass units. And these are very precisely measured. And so it's precise enough that the difference between these two numbers is real and significant. You might have overlooked it, but please do not overlook it, because that little difference of 0.03 atomic mass units is going to get converted into pure energy. We're going to be multiplying this by c squared, and let's see how much energy comes out of that. So the remarkable thing about this, and some people don't appreciate this, is just how huge c squared is. Even in these hydrogen fusion reactions, which is the most energetic nuclear reaction in nature, the most energetic reaction that exists, still, most of the mass wasn't changed, right? Only 0.03 out of 4.03 masses. In other words, only less than 1%. Only 3/4 of 1% of the mass got converted into energy. But even 3/4 of 1% of that mass getting converted corresponds to an outrageous amount of power, an outrageous amount of energy. There's the formula. There's the guide. This is E equals mc squared is what Einstein realized is the potential energy stored in the matter itself. Matter and energy are basically two different forms of the same thing, which we can call mass energy, and you can convert back and forth between them. And if I use metric units, where I measure the speed of light in meters per second, so speed of light is 3 times 10 to the 8 meters per second, c squared is going to be 10 to the 17, and I measure mass in kilograms, then I'm going to get the energy is the number of kilograms times 10 to the 17. Wow. That's the energy measured in joules or watt seconds. So that's if we keep everything in metric units here. Let's put in some numbers and see how much energy we're talking about. Let's suppose, for example, that I have 1 kilogram of hydrogen and it's going to be fused into the sun. Now this happens, there's way more than that every second. But anyway, well, we could imagine, for example, having 1 kilogram of hydrogen that we might run through a nuclear fusion plant if we manage to get one of those working, hopefully sometime in your lifetime. It was supposed to be in my lifetime, but it's turned out to be a really hard problem to control this. The only times that humans have managed to fuse 1 kilogram of hydrogen into helium is in a hydrogen fusion bomb. And the only way a hydrogen fusion bomb can get started, the only way we've figured out so far, is that we have to get the darn hydrogen so hot at first that it's well above 15 million degrees so that it'll start fusing in a thermonuclear fusion event. Unfortunately, that requires putting it inside an atom bomb. What a pain. So that's not that's useful for laying waste to your enemies, or at least threatening them, scaring the crud out of them, but it's not useful for generating a steady amount of power. So controlled hydrogen fusion has been beyond our reach so far. Someday we will get to do it. The sun does it naturally because the control is gravity, holding everything together. Gotta love the sun. Anyway, we've got this 1 kilogram, that's M, of hydrogen. Wait a minute, only 0.75%, only 0.007 of it is actually going to be converted into energy. All right, so it's actually only 7 milligrams. All right. Sorry, 7 grams of matter is going to be converted to energy. I take the 7 grams, I multiply it times 3 times 10 to the 8 meters per second, the whole thing squared, Wow, that gives me 10 to the 15 watt seconds, or joules of energy. If you want a convenient conversion, that's approximately the energy liberated by detonating 1 megaton of TNT. Yep, 1 million tons. I mean, a ton of TNT. It's pretty big. Well, actually, there was an interesting experiment that the Army did one time. They put together about 1 ton of TNT. Wired it all together, blew it up. It was a heck of an explosion. That's a ton of TNT. Don't even think about that. This little ball of hydrogen gave you 1 million tons of TNT. Okay, looks like I better go for now, but I just want you to realize that one little ball of hydrogen there produced enough power to power all of Los Angeles County for an entire day. Wow.